If you have electrons around, CO2 is very reactive. Electrochemists know that for quite a while. And actually, we wanted to use that because I had looked into CO2 activation in the 90s quite a bit. And what we were interested in to see is whether we can transfer electrons and then react the CO2 with itself, more or less, to, for example, form an oxalate. So a coupled CO2, two CO2 molecules, a dimer, with a carbon-carbon bond. Okay? And that's what I show you in the next slide. Just to remind you, CO2 is a linear molecule. As you transfer an electron, you have to go over a barrier because you have to bend the molecule. And, it becomes an unstable CO2 minus, which has an electron, which has an energy which is about 0.6 eV higher than that of CO2. And it has to go over a relatively small barrier to do that. People in the gas phases have looked at that, and Walsh has explained that in the 50s, what happens with the molecular orbitals in the CO2. Something that people have not recognized, at least that's my feeling, is as long as you have one CO2 molecule, the system is unstable. It's unstable by 0.6 electron volts. If you have a second CO2 molecule next to it, you have a CO2 dimer with one electron. It's completely stable. A CO2 2 minus is a stable entity. That is known in the literature for decades. It's stable by +9 electron volts. On the surface, when we transfer electrons, we always have several molecules around. And so transferring an electron to CO2 is not very difficult. Once you have done that, transferring a second electron may be more difficult, but it's possible. And if you did that, you'd have an oxalate. If you bring the CO2 in the right position, they form a carbon-carbon bond. I showed you that before. That's the CO2 at the surface, but we realized that this is already the reactant CO2. This is the oxalate at the surface. So the CO2 reacts, and I'll show you the proof in a second. The oxalate on the surface forms at -50 degrees. So as soon as you put the CO2 onto the surface, you can also go to higher temperature, of course, the CO2 accepts an electron, couples, and forms an oxalate. And the interesting thing is you can desorb that oxalate as CO2 again. If you do TPD, you do the same thing, you get it reversed. You're not forming carbonate and oxygen, and that CO, which would poison the rim. You can take the molecule off, put it back on the rim, put it off back on. And there's the chemistry involved, and you can show that by two things. First of all, you can do calculations, not on the big system. Hannu Häkkinen did this, and you spontaneously on the gold dimer form an oxalate in different geometries. But, and as an experimentalist, that is more convincing to me, you can completely prove this by isotopic labeling of the surface doing infrared. This is small signals, and I don't have time to go through the thing. First of all, you can see when you have the naked surface, no gold on it, there is a species forming, which is the carboxylate. And we can prove that because we can not only label the molecule, we can also label the substrate. And by labeling the substrate, we can exclude that a carbonate forms. Because if a carbonate would form, it would show up in the vibrations. Right? And it doesn't. So it's a carboxylate. If you put the gold on it, you still have that carboxylate on the magnesium oxide, but you have these two. And if you go through the details of this, one shows the carbon-carbon bond, and the other shows the carbon-oxygen vibrations and bending vibrations. So you can clearly pinpoint that this is an oxalate at the surface, and you can take reference data from clusters and so forth, from organic organometallic compounds. This is an oxalate forming. You can directly prove this. So this cluster forms actually an electron pool that allows you to induce chemistry at the rim, and you can use the SDM to see this. What we're now doing is we're going to very low temperature and trying to see the elementary steps of the first electron transfer, the second electron transfer, and then towards the carboxylate. That hasn't to the oxalate. That has not been done. But you can see that this is doable. Okay? Last part of my talk. We have been looking at oxides for quite a while, and thin films, and we've always been interested in silica. Silica is an important support and so forth, but silica, if we would be able to do this, also opens another route, and that route would allow us to do silica with dopants in them. And one important silica with dopants in them are zeolites. Now, the surface is flat, so I look at something like that as a zeolite with an infinite cavity. That may be a construction. But you can do, I show you experiments that you would not be able to do on a real zeolite, even with the most sophisticated NMR techniques. What we have done is we have made silica films on ruthenium, on many other substrates. The interesting thing is usually a monolayer forms. Silicon, 4 oxygens around it. For a chemist, that's obvious. And one oxygen can bind to the metal, and that metal oxygen bond is very strong, so you form a monolayer of that, very well ordered. You can find recipes where you you actually flip that thing around and put another one on top, and you form this. The people who are very much into graphene, they call that silicatine. I don't belong to that group of people, but when we submitted that, they suggested, the referee suggested that we cannot publish it without calling it silicatine. We didn't do it, but the editor was reasonable. So you can form this double layer, and you can differentiate between only if you look at the infrared spectrum, because from the top they all look the same. They form these hexagonal patterns, and they are very, very crystalline, very interesting. And if you put aluminum into this, then all of a sudden this hexagonal structure is broken off, and you form these other ring structures on the surface. For example, this thing, if you would take this out, cut this out from this aluminum doped thing and roll it up, it would give you a shaperside. So there is when you put the aluminum in, spontaneously, there is a particular distribution of ring sizes induced. We don't know why that is, but we would like to know why that is. And in principle, the SDM opens that possibility, because once we can recognize the aluminum from the silicon on the surface, then we'd be able to tell perhaps what's going on. And if we can change the temperature, we can even see the dynamics of that formation. Maybe that will contribute something to this interesting phenomena that you see in